All right, so in this video, we're going to just kind of do a basic example and go over how to find this r minus r prime vector. So first off, we have the general E-field equation, and I kind of want to note that this is like the same for all E-fields. Right now for this problem, we're just dealing with a point charge, but say you had like a charged surface or a charged line, this Q like would be the only thing that would change. So you would have Q is equal to like the integral of PS ds, or Q is equal to the integral of PL dl, just to find your charged area. So this is going to be, when you look at those other equations, or like Q is equal to the integral of PV dV, just to find your charged area, so the total charge. So this equation is universal. This Q is just what introduces that integral that you see in the later problems. Okay, so getting to the point here. Okay, so we're in this example, we have an electric field intensity at this point, okay, and it's due to a point charge, which is located here. So we need to find two different things. We need to find our r and our r prime, and then we're going to use them to plug into this equation to solve. We always take the destination point minus the source point. So if our destination point is r here, our source point is the origin. So we're going from the origin to r. So the math might get a little more complicated if we're not going from the origin, but let's go ahead and write this out. So our p given by the problem is equal to negative 0.20, negative 2.3. Okay, so that's our p point. And then our origin obviously is 0, 0, 0. But if it wasn't 0, 0, 0, the same math would apply. So I know that this maybe seems like we're wasting time by doing this, but I think you should know what the process is just when you're not starting at the origin, because that will sometimes happen. So it's like the x minus the x, the y minus the y, and the z minus the z. So we know our vector r is equal to OP, which means that it's going to be negative 0.2 in the x, 0 in the y, and negative 2.3 in the z. So that's our r, and that's a vector. Okay, so next, same thing here. I won't make you guys sit through all of this here. Okay, so this one is our r prime. So r prime, this prime means to the charged element. So this little prime notation up here always means that it's pointing to the charged element or related to the charged element. Okay, so we have our r and we have our r prime. So r and we have our r prime. Okay, now we're going to need to use it to find the electric fields, because as we see in our equation here, we need the magnitude of r prime, and then we need this unit vector, which is r minus r prime divided by the magnitude. So if you're trying to find a unit vector in a direction, it's always the vector divided by the magnitude of that vector. So when we plug in the unit vector, it's actually going to turn our equation into q over 4 pi e naught multiplied by r minus r prime over the magnitude of r minus r prime to the third. So it should look like kind of some of the other equations, but that's just how we're finding that unit vector. So be wary of that little AQ in the direction of charge. So it's a unit vector in the direction of charge. Okay, so we have r minus r prime. So let's go ahead and do that. And in this case, it's going to be x minus x, y minus y, and z minus z. So, okay. So then the magnitude of r minus r prime is always the square root of all of the components squared. So it's going to be, and that's going to be equal to 0.458, and we're dealing with meters in this problem. Okay, so we have the vector, r minus r prime, we have this guy, and we have the magnitude. Okay, so we found these guys. So just to recap what we did, so we were given two different locations, the point where we were trying to find the E field and the point where the charge was. So we had to find this OP and OQ, so measuring from the origin to get r and r prime. And then we had to do r minus r prime, which is just all of the x components, so x minus x, y minus y, z minus z. to find that vector, and then we found the magnitude, and the magnitude is the square root of all of the components squared. So now that we found all of our components, we're going to plug them into our E-field equation. So we have a value for Q. We're just given a number for this one, but if it was a surface or line, we would just have to integrate over the bounds of that surface or that line just to find the total charge, but we're given the total charge. This is a pretty straightforward point charge problem. Okay, so let's plug in what we have. So what we're basically going to do for this is you combine all of your numbers, and then we can kind of pull the vector out. Plus 0.437 in the z-hat direction. And this is just kind of moving numbers around. You could represent this in any way and just distribute. At this point, it's really just like a series of numbers and then multiplied and distributed by these guys. So this problem just distributed and then, rewrote them as unit vectors. So, okay. So we just went over how to find r minus r prime and what that means in terms of the direct E-field equation to find E-field intensity.